Okay, I think we'll get started. So we're going to start to learn about Lewis dot structure today, and we'll get the basic ideas down, and then we'll add some further ideas next time. And with Lewis dot structures, yes, definitely listen to these videos, but where you really get it is through practice, practice, practice. So you want to practice a lot of Lewis dot structures. Start with the easy ones, and then we'll work to hard ones. And your book will have plenty, and then you could probably find more through Google. And this is really what I think, if you had to choose one thing, which is probably not fair, but if you had to choose one thing that makes a difference between a chemist and another type of scientist, is the ability to write and understand Lewis structures. So here we're learning, we have the curriculum to be a physical chemist. So this is probably the first part that really would separate the chemistry part of that. So you definitely want to be really strong at Lewis structure. And while this seems elementary, it's an elementary theory of bonding, and we will see much more advanced theories of bonding as we go up through the curriculum. This is used all the time, and so any professional organic chemist, inorganic chemist is drawing Lewis structures. And so although it's something we learn early, it's something that we use often throughout our whole career. All right, so the central idea is that the chemical bonds are totally dominated by the interaction of valence electrons. So the inner core electrons aren't involved in bonding in the Lewis theory of bonding. So we're talking about the electrons in the outermost shell. Then with the dot notation, we draw a dot for each of the valence electrons. So here's the first row or second row of the periodic table, lithium through neon. And as we go across, we increase the number of valence electrons, and they are drawn as dots. Now, typically, if there's two of them, we'll draw them as pairs, but that can vary a lot. For example, carbon, definitely you'll sometimes see it like this. Right, that's perfectly fine, because usually we aren't drawing the dot structure for a single atom. We're drawing the dot structure within the context of a bond. So you actually don't see this very much, but this is the starting point. Okay, then the idea that drives bonding with the Lewis dot structure formalism is that when you put together these elements, you want to try to get 8 electrons around each element, and that's called the octet rule. So any valid Lewis structure is going to need to satisfy the octet rule. Now, there we see some exceptions with boron and aluminum chemistry, but everything else we go for the octet rule. And the exception there is hydrogen. Hydrogen, 8 for hydrogen is 2, because it tries to get the Lewis dot structure around it equal to its closest noble gas, which is helium, and 2 electrons. For everything else, their closest noble gas is 8, and that's the basis of this octet rule. Now we will primarily, in fact, after just the next several seconds here, we'll be working with covalent bonding. So Lewis dot structure is really designed for understanding covalent bonding, where the bonding is where the electrons are shared in the bond. We can, though, talk about ionic bonds. Here we have sodium. The Lewis structure would be like this. Neutral chlorine, the Lewis structure would be like that. As we've talked about in the last couple of lectures, the sodium would very happily give up an electron to get a noble gas configuration around it. So now it's given up electron. If we notice, all of a sudden these electrons appear out of nowhere. Once we've given up that electron, we're now back up a row, and we have the full noble gas configuration around. Likewise, this electron went to chlorine, and we reached the noble gas state, so an octet around it. And then this is negative, this is positive, so we have an electrostatic attraction between these ions. And that's the ionic bond. All right, let's get to covalent bonding. And so let's say we want to try to you could say either predict what bromine is going to be like in its natural state or explain what it's like in its natural state. So bromine is Br2. So let's explain that with Lewis dot structure. Here are the individual Lewis structures. We have an opportunity now to get an octet if we can share each of these. And indeed, that's what happens. And now we draw the Lewis structure like this. Now, what we will typically do is those that are shared are the bond, and those that are not shared are the lone pair. So this is a bond or bonding pair. And this is usually represented by a one line for every pair of electrons. And so this would represent what's called a single bond. These are called lone pairs. And in normal sort of Gen Chem level Lewis structure, all electrons are either in a bonding pair or in a lone pair. Certainly when you get to organic, you talk about electrons that are not in lone pairs, just appearing isolated, and those are called radicals. But we won't talk about those here. Okay, so with that, we often redraw this as a line. So we would go Br, Br, and then draw the lone pairs in separately. And this is what we would call the Lewis dot structure of Br2. Let's try H2O. Now I have the opportunity to share, to get an octet around oxygen, and the octet around hydrogen as the 2. So we would go like this. And we would write then something like this. And those of you who've had high school chemistry, you say, well, why is that not bent? Well, Lewis dot structure is saying nothing about geometry. So Lewis dot structure only talks about connectivity. We will quickly get to geometry, and we will base the geometry on some additional ideas to the Lewis dot structure. But the first step is getting the connectivity, and we don't worry about what the shape is in space. Okay. Let's do one more quickly. Let's do carbon tetrachloride. Chlorine all has 7 around, carbon has 4, and so we can share these, and we become this. Okay. All right, so that's kind of the basic idea. Let's go through an algorithm for getting the correct Lewis structures. And we will go through the sort of the elementary version, and then we'll add some things next time. Okay, so the first step is to determine the total number of electrons. Now, what you're thinking about here is there's a strong tendency, you have to fight this tendency, to say, I'm going to take this element from row 7, so like fluorine or chlorine, it has 7 electrons, which it certainly does, and then those 7 electrons stick with it in the bond. That's what's the misconception. Just say this, think of it as like a a potluck party where you bring a dish to share with everybody. So if you bring brownies, you're not the only one eating brownies. So you take the bromine, it comes with its 7 electrons. Those 7 electrons get brought to the molecule, and oxygen would bring 6, and so on. So that's how you want to think about it. So you know how many electrons each one is bringing from their column in the periodic table, but then those electrons get mixed around in the molecule. And then we go on with the rest of our algorithm. So we determine the number of electrons. Then we draw what's called a skeleton structure. So in this skeleton structure, we connect everything with single bonds. Generally speaking, those that, if we're looking at the periodic table, those that are up in this direction or over in this direction, down or over, will tend to be the central atom, and then the others will be the peripheral. And that's generally true unless things are with themselves. We're going to see an example here of iodine with itself. Someone's got to be the central atom. And so there's sort of these rules of thumb that you pick up as you practice your Lewis structures. But you want to start usually with the element that's heavier and further this way on the periodic table. Don't worry about cyclic structures. So all the structures that we're going to be talking about is with a central atom and then peripheral atoms. When you get to organic chemistry, and carbon can get involved in cycles, and other elements can too, but we won't be addressing that. So we've got our skeleton structure drawn. Now that is not necessarily a valid Lewis structure. It could be, but you have to assume it's not. And it either has too many electrons, too few electrons, or it has the right amount of electrons. If that's the case, then it is the Lewis structure that you would say you would present. But if it has too many electrons, then what we need to do is make double and single bonds. So if our skeleton structure has too many electrons, more than what was brought to the party, that is an indicator to us that we're going to make double or triple bonds. The case where we have too few electrons, the skeleton structure has too few electrons, there's extra electrons that the atoms brought to the party. Then we have to add those to the central atom. We'll have then broken the octet rule, and that is called hypervalency. And that can occur only if you have elements in row 3 or lower down the table. All right, so let's just practice a little bit now, and then we'll certainly come back to it in the next video, and then you will get repetition with your own practice here. Let's try carbon and oxygen. So carbon is going to bring 4 electrons, and remember we're counting only the valence electrons, and then oxygen is going to bring 6 electrons. But there's 2 of them, so this will be 4, this will be 12, and so we'll have a total of 16 electrons. Okay. So let me write that up here. 16 electrons. Now let's draw our skeleton structure. We choose a central atom, and could choose an oxygen, but the right choice here, based on these rule of thumb, is carbon's further this way. So we do this, and then we make an octet with lone pairs around everything. Now we check this. So we've got all octets, that's good. But do we have too many or too few electrons? If we have too many or too few, it cannot be the right structure. So we have to make these adjustments. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons. So what we need to do then is now take 4 away and add 2 in the form of a bond. We take away 2 lone pairs and create a double bond here. So what has that done? We've taken away 4, that would take us to 16, but we added back 2, so that takes us down to 18. Now we certainly could take from here and make a triple bond here and a single bond here. In cases like this, we could say, oh, there's some symmetry here. Why would one oxygen be more special to be in a triple bond and the other one to be in a single bond? So we can use our ideas of symmetry to say, well, these oxygens are the same, so I probably have this. Now, we will talk about next time a way to formally check that. Is it 2 double bonds, or is it 1 single bond and 1 triple bond? Okay, I've done this. I've gone down now 4. That would be 14, but I come back 2, so 16 electrons. Do I have an octet around everything? Well, I have 4 valence pair and then 4 bonding pairs, because each one of these is a bonding pair. So there's 8 around here. That's okay. Carbon, 4 and 4, that's 8. And 4 and 4, that's 8. So this is a valid Lewis structure for carbon dioxide. And so that's an example where we have too many electrons. Let's look at I3 minus. So I is going to bring 7 electrons. There's 3 of them. So that's 21. And then this is overall minus, meaning it's carrying an extra electron. So we have an electron for the charge, right? And so that's going to be 1 electron and 1. And so we have 22 electrons. So let's write that up here, 22 electrons, so we don't forget. Let's go ahead now and draw a skeleton structure. Well, iodine, not really a good candidate for a central, it wouldn't be a central ion if, say, carbon was present, or atom if carbon was present, but there's nothing else there. There's iodine, and we don't make rings, right? So we don't do this. There'd be a temptation to do this, because why would one iodine be special to be in the center? And so this would treat them more symmetrically. But I'll just say for now, we won't run into cases where there is rings. All right, so let's draw the skeleton structure. And let's count our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. But we need to have 22, so this cannot be a valid Lewis structure. It doesn't have the right amount of electrons. So I'm in a too few case here. I have to add to the central atom. And so I do this. I add an extra lone pair. I'm now at 22. And this is now the correct Lewis structure. Now notice we are not satisfying the octet rule for the central atom. And that is okay. It's less desirable, but atoms that are big enough to have d electrons, so row 3 or higher, d start with 3, can accommodate extra electrons and violate the octet rule and go hypervalent, or beyond the octet rule. And that's what happens here. So this is Lewis structure. Now, just a matter of notation, what we do with ions, because this is an ion, is we put in brackets and then put the charge above. So this, what we have drawn here now, is the final structure that you would present as a chemist for the I3 minus. So this is the first step in Lewis structure. Again, practice, practice, practice. This is so important. And just find all the problems in your book, try to work those until you feel like you're getting all of them right. We will go through now some more advanced ideas where we look at formal charge and resonance. Those are what will help us decide when we have multiple reasonable choices for Lewis structures. So this first stuff here, there's only one reasonable structure, and that just pops out with this algorithm. But there are times when there are more than one reasonable structure, and so you have to choose one. You know, if I had to guess which one, this is what I would present. And so you want to have that intuition and that formalism with the Lewis structure. And so that's coming next, and we'll just continue to practice these.